I'd like to introduce our next speaker, Dr. Raymond Corky Clinton. He is the Associate Director of Science and Technology Office at Marshall Space Flight Center, and he'll be giving us a talk on lunar research for advanced manufacturing. So welcome, Corky.
Thank you much. For bandwidth, I think I'm going to go ahead and cut off the video. Okay, my presentation today is a high-level overview of advanced manufacturing, the thrust areas, the projects, the challenges for the creation of a sustainable presence on the lunar surface. Now, for this presentation, I have broadened the manufacturing definition to include excavation, infrastructure construction, and also in-situ resource utilization. Could we have the next slide, please? Yeah, the first thing I want to do is to acknowledge those who contributed to the presentation. Start with the leadership of those areas that I just mentioned, John Vickers for advanced manufacturing, Mark Hilberger for excavation, construction, and outfitting, and Jerry Sanders for ISRU. Also the leader of the IMPACT project, that's our Moon to Mars planetary autonomous construction technology. Our partners, the architects that are supporting IMPACT, the experts that provided information on in-space manufacturing, and our microgravity researchers from Penn State. Next chart, please. Okay, we're going to start by explaining what we're doing in ISM, and then we're going to talk about why we're doing it. And then we're going to move on to the projects that are supported by the Lunar Surface Innovation Initiative. Note also what's going on with the Penn State work, quick summary, and hopefully have some time for a few questions. Next chart, please. Okay, this is a high-level view of the STMD support and the investments for technology development for exploration. It's broken out and color-coded for their 4 phases. GO is focusing on space transportation and associated technologies, and that's in green. Land is in the yellow, and that's precision landing, extreme access on the lunar surface, things like that. LIVE is in blue, and that's the technologies that are needed for a sustainable presence on the lunar surface, and then ultimately being able to explore the moon, and those are in green. Okay, these technologies, as the graphic shows, you can see the lines across there, feed forward to Mars exploration. And for the purposes of this talk, I'll be focusing on advanced manufacturing in the lower left and the lunar surface innovation elements of excavation, construction, and ISRU. I'm going to start with advanced manufacturing. Can we have the next slide, please? Okay, advanced manufacturing at the STMB level is very broad. It encompasses a broad portfolio, including 6 themes or thrust areas, like additive for propulsion, composites, digital twins. But the focus of the discussion this morning is going to be on in-space manufacturing, or as it's titled, in-space spares and repairs. And you can see the iconic picture of Butch Wilmore there holding his ratchet handle, which was actually the first part printed on space station that was uploaded from the ground. If we can have the next slide, please. Okay, in-space manufacturing is a portfolio project, and it's got 3 focal areas: on-demand metals, additive manufacturing, recycling and reuse, and on-demand electronics. And I'm going to talk more about each one of these focal areas on the following charts. So could we have the next chart, please? Okay, for on-demand metals, we have 2 systems that are in development. One is TechShot's Fabrication Laboratory, or Fab Lab. They're using bound metal deposition technologies with titanium. The other is Vulcan, and that's from Made in Space, now Redwire. Vulcan uses wire arc additive manufacturing and can basically use any materials that you can weld. Both of those have CNC for machining capability for part finishing, can print other materials, not just metallics, have some amount of inspection and monitoring capabilities, and hopefully will be able to be upgraded for printed electronics in the future. And the right-hand side lists some of the key issues and constraints for ISS, which is our current test bed, and then looking forward to the future use in deep space and on the lunar surface. And we're going to start with the materials. First of all, what's available in the regolith that we can process and use for build materials? Second, what can we repurpose on the lunar surface? Next, others have mentioned operation in the reduced gravity environment. So the physics involved in the deposition process may be different. We also have the absence of convective cooling. And we always have to be mindful of mass, power, and volume. Not only are they costly, but they're always limited. And one other key capability that I want to mention before we leave this chart, which is highlighted at the bottom, we need to be able to verify part quality. We won't have access to all the NDE equipment and the capabilities that we currently have on Earth, but we still have to know through some means that we've made a good quality part that the astronauts can use. Let's go to the next slide, please. Okay, recycling and reuse is a critical capability. It's more than just the development of the process and the hardware. It's what the chart says. It's an ecosystem. It's about purpose-built materials. The team investigated 101 materials on the cargo missions manifest for ISS. And that in itself tells a story, 101 materials. The recommendation out of that study was to pursue alternate materials for recycling. None of those materials worked as they wanted them to work. So the point that I want to make here is that the broader perspective really requires a high-level systems planning for common use materials for deep space missions. We can't use 101 materials. Now, looking forward, we're going to be able to need to recycle metals. We'll also need sterilization capabilities. Now this is very impactful because a prior study indicated that food and medical waste was a significant component of the ISS waste stream. So we'll need to be able to produce materials that are food and medical grade for those applications. Again, we'll also need verification of the recycled feedstock quality. You know, that's the first step in knowing whether or not the part that we made is a good quality part. Now, for the moon specifically, as I've already mentioned, we'll need the capability to extract feedstock materials from the regolith through beneficiation processes. Okay, next chart, please. For on-demand electronics, there's really a broad spectrum of activities going on, including the development of conductive inks, the development of multiple process technologies, development of sensors for temperature, pressure, humidity, and a variety of gases. Now, the cortisol sensor and the personal CO2 monitor shown in the center and lower right, those are examples of printed electronics that are being developed for the crew health and safety, as well as the flexible and wearable multi-sensors like the AstraSense shown in the middle right that are also in development for flight test on space station. Could we have the next chart, please? One technology demonstration that just arrived on ISS very recently is the Redwire regolith print, which was formerly known as regolith on ISS or REG-ISS. In this experiment, Redwire will be testing a lunar regolith simulant-based feedstock material in their modified additive manufacturing material, and that uses thermoplastic binder. You can see a photo of the printing process on Earth in the far right, and then right below that is compression testing of the sample. Next chart, please. Okay, I've talked about what we're doing in in-space manufacturing for the last several charts, and now we need to talk about why we're doing in-space manufacturing. We're developing these technologies because we'll need them. We'll need them as an integral capability for deep space exploration, not something that's sitting over in the corner and is a laboratory curiosity. Because unlike space station, for deep space exploration, there are no resupply missions. There's no fix and fly capability for the spares and repairs. There's no rapid abort to Earth, and mass is much more critical. So for the next steps beyond ISS, for, again, our proving ground and testing facilities, our gateway, and the lunar surface. And these sites are on our way to Mars. Now, that said, the process and material developments are necessary, but they're not sufficient. I talked just a minute ago about the need to have a comprehensive systems level planning, not just for the common use materials, but also for the implementation of additive manufacturing. This is something that we need to start at the outset of these designs, not as a drop-in replacement, but to focus on being able to make the repairs for those components with the technologies that you have on board. And that's really the whole mission in a nutshell right there. Okay, could we have the next chart, please? Okay, now let's shift gears and talk about lunar surface innovation initiatives, starting with excavation and construction. Next chart. First thing we have to decide is what infrastructure we'll need to build for a sustainable presence on the moon. Our thoughts are that the early needs are landing pads, blast shields for the landing pads, and power stations. And then as we move forward and further develop the lunar settlement, we'll need roads and habitats, consumable production facilities, and greenhouses. The next chart. Okay, we'll be starting with excavation. Excavation is critical. It's critical for the production of consumables, where you'll have robotic excavators like the Razor that's shown there in the center of the chart. And Razor and equipment like it will go and dig and transport dry and icy regolith to the processing facilities where they'll be processed into multiple products. We also need excavation for consumable construction feedstock materials. And that includes not just the raw regolith transport, but also the beneficiated materials that we will turn into binders for some of the construction materials. As others have said, the lunar environment's tough. It presents lots of challenges for humans and also for the machines. One of those is low reaction forces for the excavator due to low gravity. So to address this for the low reaction forces, Razor has counter-rotating drums, and you can see that in the photograph. And the Razor folks are counting on a 2026 tech demo on the surface of the moon. As we've talked, dust is very abrasive. It's such a problem there that there's an element devoted to that in LSII to come up with dust mitigation approaches. Autonomy is another challenge that's really common to all the systems that we'll put on the moon. And again, due to its significance, it's also an LSII focal area. Can we have the next chart, please? Okay, for construction technologies, we're evaluating multiple materials and processes. Cementitious materials that include binders that can be produced from the materials that are found in the lunar regolith, as well as water. Geopolymers, directed energy processing methods like laser and microwave sintering, and thermosets, which includes melting. The construction development faces really the similar challenges that the excavation does. Autonomy, long-term operation in the lunar environment with the dust and extreme temperatures. We also have to make sure that we have successful interfaces between the construction equipment and the excavation equipment. That's for regular feedstock transfer and conveyance, and also for the site prep. We have to be able to verify the structures that we produce, and that includes having inspection capabilities. And we also have interdependencies on other capabilities within the STMD portfolio, and that's especially for the larger and more complex structures. We'll need power, we'll need communication, we'll need navigation, and other capabilities that come from these other projects. Also, as we will need to do for the excavators, we'll need to design these systems to be repaired and to be maintained. A little bit about the graphics on the right-hand side. Those are initial architectural design concepts for habitats and landing pads that come to us from ICON and Space Exploration Architecture. And those two groups participated in NASA's Centennial Challenge for the 3D printed Mars HAB. And since that time, the Bjarke Ingels group has also joined the impact list of partners. Next chart, please. Now, this is our construction roadmap, and we're currently in phase one. developing the excavation and construction capabilities that I've just described. The circle, that's actually the second from left, is an early concept of our first construction demo, our proof of concept on the construction processes. And again, we're targeting that for a 2026 demo. In phase two, we're going to mature these technologies to enable the construction of functional structures like landing pads and habitats, and then progressing to phase three. In the upper right bullets on the top, you can see what we're calling the Lunar Outpost. What's outside of that field of view is a solar farm on the right and a greenhouse on the left. And then if you look at the blue shaded circle, what you see there are astronauts working in an outfitted habitat. We don't want to launch things like tables and chairs and ducks and so forth from the Earth. We'd actually like to construct them on the moon. And that's a really top level summary of what's in outfitting. And then finally on phase four is the background, and that's the lunar settlement. The next chart, please. Okay, before we leave this area really quickly, I want to acknowledge the work of Dr. Radlinska at Penn State, who leads some pioneering investigations on the effects of microgravity and the LEO environments on cements and polymers. For the initial cement solidification experiments on ISS, which I think completed in 2018, they found that the porosity increased with decreasing gravity. They found that the crystals were larger in microgravity. And they found that the microgravity on space station is a better analog for lunar conditions than the 1G on Earth. They'll also be launching some samples of geopolymers and cements on MISSI 15, which is scheduled to launch at the end of the month, and those samples will be exposed to the LEO environment. And they're working with DLR on another solidification experiment on ISS that's scheduled for launch in late October. Next chart, please. Okay, now we want to talk a little bit about ISRU. And I promise you'll learn a lot more from Jerry Sanders later on in this workshop. Could we have the next chart, please? This is actually Jerry's chart, and thanks to Jerry for this one. From a manufacturing and construction perspective, what this chart tells me is that the regolith, while different in different locations, has the materials that we need for feedstocks, for construction, for manufacturing, and for a future lunar economy. It has metals for spares and repairs and construction. It has silicates for the production of fibers, which can be used for reinforcements. It's got binder constituents such as calcium, sulfur, and magnesium. But most importantly, it has oxygen and water ice. And we know that from a variety of means, but most recently from the impact from the L-cross and the measurements that were made subsequently to that impact from the ejecta. Next chart, please. I've talked about this in terms of the production of consumables, but being able to produce oxygen and water, absolutely critical for a sustainable presence on the moon. Challenges to be addressed are really the same things that we've talked about before. You have to interface with the regolith system. The regolith and the excavators have to bring that. They have to handle that. They have to turn that over to the processing facilities for production of the consumables. You have to develop and scale up that process for the consumables. It has to operate for a very long time on the surface of the lunar environment, which means it has to be reliable. It has to operate in the presence of lunar dust, because you're going to have excavators scurrying around all over the place, digging in the dirt. And you have to be able to produce the quantities that will enable a sustainable presence on the Earth, on the moon, excuse me. Okay, last chart. Real quickly, hopefully the summary here is pretty clear. If we're having a sustainable presence goal for being on the moon, we have to be able to live off the land for the extent possible. And what this means is that we have to transform what's there on the left, which is on the moon, into the products on the right. And in the middle, that's where the miracle occurs. But I'll tell you, this is a great set of challenges. And I couldn't imagine any more work that's going to be more fun than creating those miracles that happen in the middle to create those products that are on the right. And that's what we're looking toward as we head back to the moon. So that's the end of my presentation. If I have time, I'll take questions, but if not, maybe in the chat. So thank you.
Great. Hey, Croaky, thank you very much for that wonderful, informative talk. I think we could take one question. It's from Anthony. It says, have there been any found sources of nitrogen and phosphorus on the moon?
I believe the answer to that question is yes. I'd have to go back to Jerry's chart. If you want to flip back to that really quickly, we can see that. But I think on the right-hand side where Jerry lists the materials, he has shown phosphorus and nitrogen. And again, he might be the better one to answer that question, or Jennifer Edmondson, who will also be on later today. One more. Let's see. Yep, I see some nitrogen there in the form of ammonia. Let's see. I'm not seeing any phosphorus right offhand.
Corky, if you don't mind me interjecting.
Oh, yes, please.
There's nitrogen in the permanently shadowed regions, and phosphorus is actually one of the parts of creep, that potassium earth element and phosphorus component found in some of it's kind of more of a geochemical signature that's found in a lot of the lunar materials. If you look at I think it's the Clementine map, the areas that are kind of more rich in that red or green color are higher in that creepy component. So you can find phosphorus in the materials there.
Thanks, Jennifer, for that information. And everyone, if you do have any more questions, please go ahead and put it in the chat and they can answer it there. I want to point out one thing before you move on to our final speaker for the day. There was a problem with concurrent session 3's link that you all received. And so if you go to the chat, the updated link to concurrent session 3 for today is listed there. So please go ahead and if you plan on attending concurrent session 3, please take a look at the chat for the update. And thank you. And Corky, again, thank you for that wonderful talk.